All right, let's talk a little bit about infinite limits. So, infinite limits, they'll occur whenever you're going to have an equation where it's not going to necessarily converge on a specific number, where it's just going to keep going and going and going and going and going. Um, well, oftentimes you'll see these with rational functions or anything that has like an x in the denominator. So let's take a look at kind of maybe a real quick example. Let's say if you have f of x equals probably the most basic one is just this 1 over x. So if you have an equation like this, let's kind of think about the behavior as x gets really, really, really small. When x gets really small, like let's say, we'll do like 1 divided by 0.000001. Right? So that's going to be a really big number. And if this kept going and going and going, f of x would just get larger and larger and larger. And to the point where, since there's no stopping how many numbers you could have after this decimal place, I mean, this goes on forever and ever. So in that same way, the value of f at these really small numbers is going to get really, really big. So let's say, to the point where we couldn't, say there's no end to it really. So we're going to say, well, let's say what happens if we take the limit as x approaches 0 of 1 over x. And what would this look like? Well, let's take a look at it graphically, because oftentimes these can be really helpful to see. So, whoops, that's not typing. Y equals 1 over x. There we go. All right, so let's see there. Let's scooch this down a little. So you'll notice as it gets closer and closer to 0, this is going to approach your y-axis, but it's never going to cross it. It's just going to get, because closer and closer and closer is just going to mean the more vertical your line's going to get. And then once you jump over this axis, the same thing with a negative. Let's say you have a negative number, like negative 0.0001 on the bottom. Well, that's going to be the same kind of an idea, except this is going to be negative. So let me just kind of sketch this out real fast for us. So right over here, I'll just give us a brief little visual so we can see what's going on. All right, so it's just going to go like this and up, and then it's going to come in like this and up as well. All right, so looking at this is 0 right here. So we're looking at the limit as 1 over x approaches 0. Well, we have a problem here. See, well, just because it's not going to approach the same number, right? Remember, to be a true limit, you have to have the same number, it has to approach the same number coming from this way, coming from the right, as it does to the left. So technically, this limit wouldn't exist. But we can help ourselves out a little bit by saying, well, let's say instead of this, so this would be like that, we could have the limit as x approaches 0 from the right of 1 over x. Now, there we're coming in this way, so you see how it gets positive. And it's going to get positive and positive and positive, more and more and more. So in that case, that limit's going to be positive infinity. And then likewise, approaches 0 from the left, then that's going to get more and more and more negative the closer that we get to 0. But it's never going to actually hit on 0. So that is negative infinity. So this is what we'd call an asymptote. It'll approach it and it'll get close to it, but it will never actually be at 0. So typically you'll see these as again as rational functions. You can determine them analytically, and that just uses a little bit of algebra. Let me give us a good let me think. Put let's say you have I don't know, maybe x squared plus 1 over x squared minus 1. That's one that I've seen a couple times. All right, I'm going to move the camera down just a little bit. Okay. So let's say you have something like this. Well, remember back to one of your algebra classes where you say, well, you can't really divide anything by 0. Remember, you can, it's just bad math to do that. So if you look at this, you can figure out what these asymptotes are pretty easily just by factoring. So this is going to stay the same. And then down here, I have a squared value here, and 1 is a squared value, so I have a squared value there, and I also have a minus sign. If you have a square value minus a square value, then you can easily factor that. So plus the square root of this, and minus the square root of it. So, so there we go. And now, looking at this, we say, well, I can't have this be 0, because if this is 0, no matter what this is, this could be 5 bazillion, it doesn't matter. This is still going to be 0 because I'm multiplying it. And likewise with this, if this is 0, it doesn't matter what this is going to be. So more than likely, if I was looking at this, I could say, well, my asymptotes are probably going to be at the values of x equals -1 and x equals 1. So let's just take a look at this graphically and see. And honestly, if you're doing these practically, graphing is usually the way to go, just because then you can kind of visually inspect them. So I'll have y equals x squared plus 1 on the top divided by x squared minus 1 on the bottom, and let's see what this looks like. All right, kind of a cool looking graph, I'd say. So coming in here, here's our value of 1, and here's our value of -1, and you can see just by inspection that these values are going to be, or this is going to be where your vertical asymptotes are. So looking at this, we would say, well, there's no limit as x approaches 1, there's going to be no limit for as x approaches 1, again, because they don't go to the same value, right? However, if you say, well, as x approaches 1 to the left, you'd say, well, that's probably -infinity. Value as x approaches it from the right for 1, that's probably positive infinity. You can do the same thing for this -1 over here. So if you're doing these analytically, one of the first steps is factor everything as much as you can, like we did, and then that will give you your asymptotes, and then you can graph it and see where the graph behaves or how it behaves at those asymptotes to see if it's going to be either a positive or a negative infinity for your limit. All right, one last thing, these are not just rational functions that you can do this with. Let me whoops. Okay, let's just delete. All right. What's a good one? How about let's do cotangent. Cotangent also has asymptotes. You can see here that it kind of squiggles down, jumps up, squiggles down, jumps up. And this is going to squiggle down and jump up on multiples of pi. So your asymptotes are going to be 3.14, whatever 2 pi would be. And negative as well, 3.14 and 2 pi. So this is just kind of to show you that when we're finding these infinite limits, it doesn't necessarily have to be a rational function, although typically that's where you see it. So all right, so graph them. That's going to be your best friend on this one. And remember, in order for it to have a limit at the specific value, that they have to converge on the same value. If it's not the same, then then it's going to be no limit. And what I mean by that is you'll see it like if you have a graph here, let's say here's your graph, and then you've got some kind of an asymptote here, and if they come up like this, and this side also comes up like that, right? You know that it's converging at the same point. It just doesn't ever necessarily have a specific point. It's gonna, like, say this goes on and on forever and ever. Well, then let's just say if this is A, so then the limit of as x approaches A exists, right? Because it's converging on the same one, as opposed to, like in this example up here, we had it where it doesn't exist because they're not converging on the same value. So keep that in mind. That should hopefully be a pretty good start, get you going on these infinite limits.